بسم الله الرحمن الرحيم. بنرحب فيكم في محاضرة رقم 18 في الإجراءات إشارية رقمية. المحاضرة هاي بتتكلم عن بعض ال properties of the region of convergence for the Z transform. Properties of the region of convergence for the Z transform. اوكي، first property يمكن من المحاضرة السابقة وجدنا بعض الملاحظات على ال properties of the ROC. يعني the ROC is a ring or disk in the Z-plane. So it's a ring or a disk in the Z-plane centered at the origin. Okay. إذا ال ROC دائما عبارة عن Z-plane. It's either a disk or a ring somehow, so centered always at the origin. Okay, so this is the property number one. Property number two, the Fourier transform of x of n converges absolutely if and only if the ROC, the region of convergence of the Z transform of x of n includes the unit circle. So if the ROC contains the unit circle, let's say that you have a region of convergence saying that you have a pole at 1/2 and you are outside this pole. So the unit circle is with the radius r equals 1. The unit circle of r equal, if it is included within the region of convergence, then the Fourier transform also converges absolutely and it exists. Okay, property number 3, the region of convergence cannot contain any poles. So no poles should exist within the region of convergence. So if you have, let's say, a pole here at, let's say, 1/2, then this cannot be the region of convergence, because at the pole, the x of z diverge to infinity. Okay. Property number 4, if x of n is finite duration sequence, then the ROC is the entire z-plane except possibly z equals 0 and z equals infinity. Okay? So if x of n is finite duration sequence, the region of convergence is the entire z-plane except possibly at z equals 0 and z equals infinity. Okay. Property number 5. If x of n is right-sided sequence, the ROC extends outward from the outermost finite pole in x of z to infinity. So it's from the outermost finite pole to infinity. This is the ROC, the ring that goes from the outermost at 1/2 and goes to infinity if you have only one pole in the x of z. Okay, 6, the opposite. If x of n is left-sided sequence, the ROC extends inward from the innermost pole in x of z to z equals 0. So if you have a right-sided sequence, it extends outward. If you have a left-sided sequence, it goes inward. Okay. If x of n is a two-sided sequence, if x of n is a two-sided sequence, then the ROC will consist of a ring in the z-plane bounded by bounded on the anterior and exterior by a pole bounded on the interior and exterior by a pole and not containing any poles. Okay. So you can imagine something like this. If you have 3 poles, let's say 1/3, 1/2, and 2/3, you have 3 poles. So the region of convergence could be the interior of 1/3, between 1/3 and 1/2, between 1/2 and 2/3. So, or it could be from 2/3 and outside. Now, for the two-sided sequence, it's either this one. So this is one scenario of the two-sided sequence, and the other one is the other ring that is bounded by 1/2 and 2/3. So this one is also a possibility for a region of convergence. So you have 2 possibilities of a region of convergence, either the black ring or the red ring that we have here. Okay. The last property, which is also an important property for the region of convergence, is that the ROC is a connected set. Eight, the ROC must be a connected region. So it must be a connected region. So we cannot say that this ring, this disk inside, union this red ring, and you have not connected within this. So you cannot say that the inside of 1/3 as a region, union the region between 1/2 and 2/3. These are not connected, so it cannot be a region of convergence. Okay. Now we'll talk about the inverse. The inverse Z transform. And when we talk about the inverse, we will do it by inspection. So we'll do it by inspection using partial, fraction, expansion, and tables. Okay, so we will assume that we have x of z is a rational transform or rational polynomial in z. You have summation from k equals 0 up to m b sub k z to the minus k divided by summation from k equals 0 up to n a sub k z to the minus k. So you have a polynomial in z. This one is b0 plus b1 z inverse plus b sub m z to the minus m over a0 plus a1 z inverse plus a sub n z to the minus n. So we have a polynomial in z, rational polynomial of z, and we would like to do the inverse by looking by table lookup, a lookup table. We have to have a lookup table. Look at the table and go by inspection and find the inverse of the z transform. Now we have 2 cases. The first case, if m is less than n, so we can say that x of z has the polynomial in the denominator is the order of the polynomial, so the order is higher than m. So this is a proper polynomial, and so we call it proper polynomial, and this is can be done by partial fraction expansion 1 minus d sub k z inverse for k equals 1 up to n. So you have a1 over 1 minus d1 z inverse plus a2 over 1 minus d2 z inverse plus a sub n over 1 minus d sub n z inverse. So this is our x of z, and we will find those ak constants by partial fraction expansion. Ak is usually found by 1 minus dk z inverse times x of z evaluated at z equals dk. Okay? So this is how we can find those coefficients or constants by the partial fraction expansion, and I know that most of you know this from calculus actually, when you do integrals by partial fraction expansion. If m is greater than or equal n, so if the order of the numerator is higher than the order of the denominator, then we will do long division. And here we have to have x of z equals to summation of br z to the minus r for r equals 0 up to m minus n plus the partial fraction done for the rest or the residue after doing the long division process for the two polynomials, the numerator over the denominator, and here we have ak over 1 minus dk z inverse. Okay? Okay. I will do an example that includes this one because it has this one also inside of it. So this one is partial fraction expansion, and here when you do the long division process, you end up with the process of dividing the two polynomials plus the residue, and we will do the residue by the partial fraction expansion. Okay, I'm going to do this example, and let's see together how we are going to implement case number 2. Okay, we have x of z equals to 1 plus 2z inverse plus z to the minus 2 divided by 1 minus 3 over 2 z inverse plus 1/2 z to the minus 2, and the magnitude of z is greater than 1. If we look at this polynomial, we have this m, the m order of the numerator is equal to the n order of the denominator. The second order polynomial, magnitude of z is greater than 1. This will help us in the region of convergence, which means that you will have right-sided sequence. So you have a right-sided sequence in your answer. Okay. Before we do this, we have to do a long division to get this polynomial here. So I'm going to do this until we have an order of the numerator less than the order of the denominator. So we'll do one step of long division. So this is z minus 2 plus 2z inverse plus 1 divided by 1/2 z minus 2 minus 3/2 z inverse plus 1. And here I'm going to multiply by 2. So 2 times 1/2, this is z minus 2, 2 minus 3 z inverse, 2 times 1 plus 2, and then we subtract. So this is minus plus minus. So this will cancel, and you will have here 5 z inverse minus 1. Okay, 5z inverse minus 1. Now, we look at the residue. If the residue has an order, the residue here has an order of minus 1. The order of the denominator is minus 2, so we will stop. Once we have an order less by 1 from the order of the denominator, then we stop. And we will have x of z now equals to 2 plus 5 z inverse minus 1 divided by the 1 minus 3/2 z inverse plus 1/2 z to the minus 2. So this is the process of long division. Now we have this BR, and BR is the only coefficient. You have R equals 0, so it's 2 BR B0. This is the one that we have, z to the minus 0, so this is 2, and we stop here. This order now is less than this one, so you have a proper polynomial, and you do the partial fraction expansion of this one. Okay, so we can say that this is equals 2 over plus z minus 1, 5z inverse minus 1 divided by 1, 1. You have 1/2 z inverse, and you have here minus z inverse. So this is the factorization of this second order polynomial. Now we can say that this is equals to 2 plus a1 over 1 minus 1/2 z inverse plus a2 over 1 minus z inverse. So this is our x of z. And we'll find a1 by the partial fraction expansion. So a1 is equal to 2 plus a1 over 1 minus 1/2 z inverse plus a2 over 1 minus z inverse. We will multiply this by 1 minus 1/2 z inverse, okay? And we substitute this at z equals 1/2 at dk, okay? So if you multiply this by 2, substitute at 1/2, this is 0. Here, 1 minus 1/2 substituted, but 1/2 is 0, multiplied by a2 is 0. And the only one that this one will cancel with this one, so you have a1. So a1 is equal to this. And this is from the other side, we are going to have this. So this is equals to, I'm going to put it in this form, and this is also equals to 2 plus 5z inverse minus 1 divided by 1 minus 1/2 z inverse times 1 minus z inverse multiplied by 1 minus 1/2 z inverse substituted at z equals 1/2. This is the other side, and this is also equals a1. So this is from this side here, and this one is equal to this one. So we substitute it here. So this one will cancel with this one, and we end up with, so, and this one will also cancel with this one, and we will have A1 equals to 5 times Z inverse, it's 2 minus 1 divided by 1 minus Z inverse, it's 2. So this is equals 10 minus 1, 9 divided by minus 1, so this is minus 9. So A1 is equal to minus 9. Okay? If we do the same thing for A2, so A2 is equal to 2 plus 5Z inverse minus 1 divided by 1 minus 1 half Z inverse times 1 minus Z inverse multiplied by 1 minus Z inverse and apply that Z equals 1. So this will cancel with this one, but this one will multiply by this one and apply at Z equals 0, so that it's equal to 0. And A2 now is equal to 5 times 1 minus 1 divided by 1 minus 1 half. So this is equals to 4 divided by 1. So this equals to 8. Yeah. So now x of z is equal to 2 minus 9 over 1 minus 1 half z inverse plus 8 over 1 minus z inverse. And here the magnitude of z is greater than 1. Notice that here you have two poles of the system. One pole is at 1 half and the other pole is at 1. And our region of convergence is with the outermost pole and going outside for z up to infinity. So the magnitude of z is greater than 1. This is the region going from a radius, circle of a radius of 1 and going out to z equals infinity. This means that you have to have a right-sided sequence. And the right-sided sequence means that your x of n should be a right-sided sequence. So it's a combination of right-sided sequences. The first one is 2, and 2 for x of n, this means that this is 2 delta of n for the constant, minus 9 1 half to the power n mu of n. This is a right-sided sequence, exponential, plus 8 times 1 to the n mu of n. And 1 to the n is mu of n. So this is, we can say that this is 2 delta of n minus 9 1 half mu of n plus 8 mu of n. If you want to combine the mu of n together, you can also put it in a nice form. Plus minus 9 1 half to the n plus 8 mu. So this is our right-sided sequence for this transform, for this x of z. Okay, so with this we conclude our lecture today. Thank you very much, and we'll see you next lecture. We'll talk about the properties and theorems concerning the z transform. Thanks.